Hello, today we're going to be talking about the Pauli exclusion principle. This principle was developed in the early 1900s by an Austrian physicist by the name of Wolfgang Pauli. The principle states no two electrons can have the same set of quantum numbers. To start off, I'm going to briefly go over quantum numbers with a brief description of what they are. Previous to this video, another set of videos was created about the quantum numbers that go more in depth about what they are. If you want to check those out, feel free to. This is just a brief overview that I'll be giving just so you, so quick refresher so we can really understand the Pauli exclusion principle. So first off, what are quantum numbers? Quantum numbers are entities like energy and charge that have been given values to measure them. We're going to focus on 4 quantum numbers today, the first being the principal quantum number, which determines the energy level or the distance that an electron is from the nucleus of an atom. Its symbol is N, and the possible values for it are 1, 2, 3, 4, so forth. The higher the value, the farther the electron is from the nucleus. The second quantum number is the angular momentum quantum number, and it determines the shape of the orbital of the electron, and its symbol is L, and the possible values for it is 0, 1, 2, 3, and so forth, until you get to n minus 1, so it's always going to be 1 less than the principal quantum number. And then the third quantum number is the magnetic quantum number, which determines how many orbitals are in a subshell, and its symbol is M sub L, and the possible values for it are -1, or negative L, I should say, to positive L, and all the integers in between those. And then the fourth quantum number is the spin quantum number, which determines the spin of an electron, and its symbol is M sub S, and the electron can either have a positive 1/2 spin or a negative 1/2 spin. Now, you may be wondering how quantum numbers apply to electrons. We mentioned it a little bit about the spin and the distance from a nucleus. So this next part, we're going to put all the quantum numbers together, state what they mean for the electrons, and then tie the Pauli exclusion principle into the physical world around us. So first off, if we look in the center of the screen, we can see these sets of numbers kind of look like coordinates that you might see for a graph, except some more integers. So I'm going to briefly explain which each of these numbers in this set are, and then I will explain what this means for the Pauli exclusion principle. So this first one represents the n, or the principal quantum number, so it's in the second energy level. And then the second one is the L, and it's 0, one of the possible L values. This third one is the M sub L, and then this fourth one is the spin of the electron. And so when you put all these quantum numbers together into a set, it's stating where the electron is around the nucleus. So it's stating its position. So if we refer back to what the Pauli exclusion principle states, says no two electrons can have the same set of quantum numbers for one atom. And so we know for, say, example, I don't know, carbon's not going to have an electron with this set of quantum numbers twice. So an electron with this one and the same one, because that would mean that the 2 electrons are in the same space. And we know that objects can't occupy the same space. If I had a rock in my right hand and a brick in my left hand, and I try to put the rock into the brick to occupy the same space as the brick, it wouldn't happen. So that same principle applies to the electrons, and is what the Pauli exclusion principle is stating. And so we can use the Pauli exclusion principle now to understand why some things are the way they are around us. So we all know that atoms occupy volume and that matter takes up space that it doesn't fall in on itself. And I don't know if we've ever wondered why that is, but today we are going to talk about the why. And the why is explained by the Pauli exclusion principle. So we know since electrons can only have one set of quantum numbers, that they're not going to exist in the same space, that the electrons are going to have to expand outwards from the nucleus and get farther and farther away the more electrons there are around a nucleus. They all can't all be around the nucleus. If they did that, then the atom would take up significantly less space, and we would see matter falling into itself. This principle also applies in space with stars like neutron stars and white dwarf stars, and it helps them be stable. Their cores are stable because of this principle. This principle is found in what's called the electron degeneracy pressure. And because the electrons are moving outwards and not all surrounding the nucleus, the electrons being in places further away from the nucleus creates a pressure which exerts outwards from the cores of these stars, which acts as an opposing force to the gravitational force, which is pushing inwards, thereby stabilizing the center of the stars. Now, if the gravitational force overcomes the electron degeneracy pressure that's being exerted outwards, the core is going to collapse and a black hole is going to be formed. Now, that's all we're going to talk about today about the Pauli exclusion principle. I hoped it was helpful to understand a little bit more about it, what it was, as well as how it applies to the physical world around us. If you are interested in learning more, here are the references where you can go to learn more. Thank you for watching.